What if the seas keep rising? A curious nova journey into the future. Right now, along every coastline on Earth, the ocean is a little higher than it was on the day you were born. You can't see it from one tide to the next. The water rolls in, the water pulls back. The beach looks the way it always has. But underneath that familiar rhythm, the whole sea is climbing, slowly and quietly. And it is climbing faster today than at any time in at least 3,000 years. So let me ask you three honest questions. How high will it go? How fast? And what would it really do to the world you live on? Let's start with how we know it's happening at all, because this is not a guess. Since 1993, satellites have measured the height of the entire ocean surface, again and again, to within a few millimeters. It is one of the most carefully watched numbers in all of science, and the trend is not just up, it is bending upward. In the early 1990s, the sea was rising at about 2 millimeters a year. Today, that rate is about 4.5 millimeters a year. In other words, the speed of the rise has more than doubled in 3 decades. Added up, the global sea now sits more than 10 centimeters higher than it did in 1993, and the year 2023 set a new record high. Then 2024 climbed even faster than scientists expected, according to NASA, mostly because the water itself was warming and swelling. The sea is not just rising, it is accelerating. And a few millimeters a year may sound like nothing, but sea level rise does its damage at the edges. It is not the calm water you have to worry about. It is where the high tides now reach, and where the storm surges now begin. Every centimeter the baseline creeps up, the floods of the future start from higher ground. So where is all the extra water coming from? 2 completely different engines are lifting the ocean at once. The first engine is simply heat. More than 90% of the extra warmth our planet traps gets soaked up by the oceans, and water, when it warms, expands. Each drop takes up a little more room. Spread that tiny swelling across an entire ocean, kilometers deep, and it adds up to a real, measurable rise all on its own, without a single ice cube melting. Scientists call it thermal expansion. The second engine is melting land ice. Not sea ice, which already floats and does not change the level when it melts, but ice sitting on land. The mountain glaciers, and above all the 2 great ice sheets, Greenland and Antarctica. When that ice melts, the water runs off the land and into the sea, and the sea goes up. Here is how the 2 engines compare. From 1901 to 2018, thermal expansion drove about 38% of the rise, and melting glaciers about 41%, with the polar ice sheets making up most of the rest. But the balance is shifting fast. The contribution from Greenland and Antarctica was about 4 times larger in the 2010s than it was in the 1990s. The ice sheets are waking up, and that matters enormously because of how much water they are holding. Let me give you the numbers because they are almost hard to believe. If Greenland melted completely, it would raise the global sea by about 7.4 meters. That's enough to redraw the coast of every continent. And Greenland is the small one. If all of Antarctica melted, it would lift the ocean by about 58 meters. 58. That is not a flood. That is a different planet. Now, nobody is saying all of that will melt soon, but you don't need all of it. And this is where one glacier in particular keeps climate scientists awake at night. Its name is Thwaites in West Antarctica, and it has earned a nickname, the Doomsday Glacier. Thwaites is roughly the size of Britain, and right now it is losing about 50 billion tons of ice every year. On its own, the water locked in Thwaites could raise global sea level by about 65 centimeters. But that is not the real fear. The real fear is that Thwaites works like a cork in a bottle. It sits at the edge, holding back the much larger West Antarctic ice sheet behind it. And researchers like Ted Scambos have warned that if Thwaites collapses, it could destabilize that whole region, eventually driving the sea up by more than 3 meters over the coming centuries. One glacier, pulling the cork on 3 meters of ocean. And if that still feels abstract, like a model of a future that might not arrive, here is the part that should settle it. We know the ice can go because it has gone before. The last time our planet was just a degree or two warmer than today, about 125,000 years ago, the sea stood roughly 6 to 9 meters higher than it does now. Same kind of planet, same kind of warmth, a coastline meters above where yours sits today. The ice sheets have done this before, and they remember how. Now you would think that if Antarctica melts, the seas would rise the most near Antarctica. And here is the first thing about sea level rise that feels completely backward. It doesn't rise evenly at all. In fact, near a melting ice sheet, the local sea can actually fall. The reason is gravity. An ice sheet is so massive that it pulls the ocean toward it, heaping the water up around its own shores. When that ice melts and loses mass, its gravitational grip weakens, and the water it was holding close goes sliding away across the planet. Scientists call this a gravitational fingerprint. So when Antarctica loses ice, the sea near Antarctica can drop, while the water piles up thousands of kilometers away. Melting at the bottom of the world raises the sea more along the coasts of the northern hemisphere, places like the United States, by roughly 30% above the global average. The ice that drowns your city may be ice on the far side of the Earth. So with all that in motion, how high are we actually heading? The clearest answer comes from the Intergovernmental Panel on Climate Change in its 6th assessment. By the year 2100, if humanity cuts emissions hard and fast, the likely rise is about 28 to 55 centimeters above recent levels. If we keep burning fossil fuels at high speed, it's about 63 centimeters to just over a meter. Push the clock to the year 2150, and the high emissions range climbs toward nearly 2 meters. But the panel adds a warning, and you should hear it clearly. There is a low probability, high impact possibility that the scientists cannot yet rule out because the physics of collapsing ice is so uncertain. If the great ice cliffs of Antarctica begin to break apart in a runaway cascade, then a rise approaching 2 meters by 2100 and as much as 5 meters by 2150 is not off the table. That is the tail of the curve. It is unlikely. It is also the reason no one is relaxed. And the stakes are not small, because so much of humanity lives right at the water's edge. Roughly 230 million people today live within just 1 meter of the high tide line. Over 1 billion live within 10 meters of it. We did not build our world back from the sea. We built it right up against the sea, in the great port cities and river deltas, exactly where the rising water arrives first. So let's leave the projections and look at where that water is already changing lives today. Start with Jakarta in Indonesia, one of the fastest sinking big cities on Earth. Parts of it are dropping by several centimeters a year, because as the city pumps groundwater out from under itself, the land collapses downward at the very moment the sea is pushing upward. The two effects together have become so severe that Indonesia is now moving its capital off the island entirely to higher ground on Borneo. In Miami, Florida, the water now floods the streets on clear, sunny days at high tide with no storm in sight. They call it king tide flooding, and it has surged as the baseline sea has crept up. In Venice, the rising water forced the city to build a multi-billion euro system of mobile barriers, called MOSC, that rise out of the sea floor just to keep the old city dry on the worst days. And for low island nations like Tuvalu and the Maldives, where the highest natural ground is only a couple of meters above the waves, this is not about wet streets. It is about whether the country physically continues to exist. Tuvalu has begun building a digital version of itself to preserve its nation even if the land goes under. And there is a quieter kind of damage that arrives long before the streets go under. It's called saltwater intrusion. As the sea pushes higher, it seeps inland underground into the fresh fresh water that farms and cities depend on. It poisons drinking water wells. It turns rich farmland salty and barren. In river deltas like the Mekong and the Nile, this slow, invisible flood of salt can ruin the land for crops while it still looks, on the surface, like perfectly dry ground. And here is the hardest twist of all. Even if every smokestack and tailpipe on Earth went silent tomorrow, the sea would keep rising for centuries. There are two reasons. First, the deep ocean has enormous thermal inertia. The heat we have already added is still working its way down into the cold depths, and the water will go on expanding for hundreds of years as it does. Second, the great ice sheets have momentum. Once a glacier like Thwaites begins to retreat past a certain point, it can keep going on its own, long after the trigger is gone. We have, in a real sense, already committed the planet to a certain amount of rise. The question that remains is not whether the sea will climb, but how high, and how fast we let it. So let me bring this back to you, standing on that ordinary beach. The line where the land meets the water feels like the most permanent border in the world, but it never has been. Over the deep history of this planet, that line has wandered up and down by dozens, even hundreds of meters again and again. What is different now is the speed, and that, for the first time, the rise is being driven by us and watched by us in real time. The coastline is not a fixed edge. It is a slow tide, moving across generations. And the strangest part is that you are living inside the moment when that tide turned and started measurably to come in. This has been Curious Nova, curiosity across time. I'll see you on the next one.